I don't know why the microphones. Microphones. Hmm. Right. So let me share my screen. Okay. So yeah, hello everyone. This is the second class of this TA class on this electromagnetic theory. And so I'm Sauravi. I'm a PhD student at IIC. It's a part of the PMRFTA ship that we are trying to uh, do here. So in today's class, if you first remember what we discussed in the last class, yes, we just had a basic idea about vector analysis, what gradient divergence curve is, and then we talked about Coulomb's law, how to use Coulomb's law, right? The basics. So today we'll follow up with it. But before I proceed, I wanted to also ask you guys, do you have any discussion forum? I think last time there was some questions in the chat asking about some discussion forum or something. So do you guys already have one such discussion forum for the NPTEL course? Okay. Okay. So there isn't any. Okay. Because I was just having this idea that you might already have some discussion forum and I would have thought of, how to join that. Okay. Anyways, so let us get going. So first, uh, we'll slightly look into, the physical understanding of gradient divergence and curl before proceeding forward. So here, this is the definition that we talked about, mathematically, right? This, if you have some scalar, you have this differential operator, you have, and like this is the gradient, this is the vector quantity that you get. This talks about how fast, it talks about the direction of the fastest change of the scalar quantity. And then you have divergence, right? If you have some vector, then you vector field, then you define or you characterize the field in terms of the divergence or the curl. And this is how the divergence look like. This is how the curl look like, right? And these are some of the important formulas regarding vector calculus. And here, as you can see, so as I was checking the last year's assignments, there are direct questions also from, this uh, formulas or identities. So and it's also important to remember these things because this comes handy in solving different questions, right? So you can actually try to prove this, and that will also give you a better understanding of why uh, why these theorems exist. So, anyways, now let us look at actually what this gradient is all about. So here, if you have some scalar quantity, right? So this is just a question, and through a question, we'll try to understand. So here, when we do grad phi, so this is some scalar quantity, and if you are asked to find the gradient of the scalar quantity at some particular point, right? Uh, what is there? Some question. Okay. Hmm. So, and you want to find at a particular point, gradient of some scalar quantity at a particular point, right? So how do you do it, right? You know the mathematics of it. So basically you apply this operator to your scalar quantity and what you get is a vector, right? Now, what does this vector tell you? It has a direction, right? Now, what is this direction actually? So if you are asked that to show that grad phi actually is a vector perpendicular to the surface where phi is equal to some constant, right? So that means if you have some surface and you have some scalar field defined on the surface such that the scalar field is constant on the surface, del phi, or basically grad phi, sorry. So grad phi will actually give you the direction perpendicular to that surface, right? And that is the direction of maximum change. That's what we read in also in the definition of while we were solving about gradient, right? So how do you prove it? Is that if you take any position vector on the surface, right, and you take basically a line element, so you write it as dxi cap plus dyj cap plus dzk cap, right? And this lies on the surface where uh, the surface over which you want to find your gradient. So you have taken a point on that surface, and now you know how what the definition of d phi will be like, right? So phi is some function of x, y, z. So if you just use the concepts of partial differentiation, you know how d phi should look like, right? It's del phi del x into tx plus del phi del y dy plus del phi del z dz. And now if you consider that d phi is equal to 0. Why? Because you have on the surface your phi is constant. So d phi should be equal to 0. And that means you can also write it in terms of a of vector scalar product. How do you write it? So you take these two vectors, right? So if you do a scalar product between them, you would get this. Now what is this? This is nothing but our gradient, right? This is the gradient of phi. So that is telling you gradient of phi dot dr is equal to 0, which means gradient of phi is perpendicular to the surface where phi is constant, right? So this gives you a physical, you know, what do I say, outlook about how gradient of phi should be directed. So if you are given any surface and if you are asked to find unit normal, and these things can come, quite useful while you solve any mathematical physics question, and obviously it will come at some later point in EM theory as well. So if you want to find the unit normal to some surface, you first do the gradient, and then you take the unit vector along that, right? So that gives you the normal to the surface. So this is about the direction of the gradient of any scalar quantity, and it's the direction along which phi is considered to change or have the maximum change, right? Okay. Now, talking about divergence. So what do you mean when you say that, divergence of some vector quantity is actually 0? So what do you mean by that? So this is just an example to understand that. So here, if you have some fluid, see, in fluid, you have particles moving, so you can consider that to have a velocity field, right? And velocity field is also a vector field. And this concept will also be, can also be translated to any other vector fields. So when you talk about electric field lines, magnetic field lines, this same concepts of underlying concepts of what divergence mean will always be valid there as well, right? So here, when this is just an example to understand what divergence will physically be related to. So if you have some fluid and it's moving with some velocity, and now if you take some point P inside this fluid element and consider a volume element around it such that the sides are dx, dy, and dz, right? So that means if you consider that your velocity now has some gradient along x, y, and z, so you can say that at this point P, if the velocity is v1, somewhere on this surface, which is at a distance of, dy by del y by 2, you'll have some different uh, velocity, right? Similarly, you'll have a different velocity on this surface because of, this dependence, del v, del y dependence. Similarly, along x, you will have a different, like if you go along y, am I saying something wrong? Okay, no. So what do I mean is, so here, if you consider this surface, suppose AFED, right? So where is F? AFED, right? So if you consider the velocity, x component of velocity there, so you know that if there is some velocity dependence on x, y, and z, so this is how the velocity should look like on that surface. Similarly, on this surface, which is GHCB, so GHCB, it will have some different velocity component. And similarly, you'll have different velocity components along all these surfaces. So you can calculate what is the fluid that is entering a surface and what is the fluid that is leaving the surface, leaving the other side of your volume element, right? So from here, you can say that the loss in volume will be like along x direction will be given by this quantity. Similarly, the loss in volume along y direction will be given by this quantity, and similarly for z. So if you want to find the total loss, you'll find something like this, right? You add up all these losses, and then you see that in the limit of, this quantity is going to zero, what you get is this term here, right? Del V1 dx plus del V2 dy plus del V3 del z. So, so that means this is nothing but your divergence. So what you're getting back is divergence. So what this is telling you is that if you have some vector field where, there'll be some flux, influx, and there'll be some outflux. And now if you say that what you have in a volume element is conserved, right? In those case, that vector field will have the divergence of zero, right? So this is same as the continuity equation for an incompressible fluid. Okay, so that's how these things are translated to physical situations. So now this is just a question. So if you are said, if you have questions like this where you have some vector given with some unknowns, some variables, and you are said that it's solenoidal. So by solenoidal, it means that the divergence of that vector field is zero. That vector is zero. So what you do is you find the divergence and then you can find the variables. So just remember that solenoidal means the vector is divergenceless. So divergence of V is zero. Okay. Now, what do you mean by curl? So curl, as the name suggests, it talks about how the vector field circulates or rotates about a given point, right? So just a convention that if the flow is counterclockwise, it's taken as positive. If counterclockwise, it's taken as negative. Now, how this concept of curl becomes important is also because will be more clear if we try to solve this first. So if you have some vector, okay, and it is said it's irrotational, so that means the field lines are not rotating. So what you mean is curl of V is zero. So solenoidal means, so what is a solenoid? Basically, it's called solenoidal because you see that whatever field lines leave comes back. So that means divergence is zero. When you have irrotational field, that means there is no curvature or turning of your field lines. So that gives curl of V to be zero. So if you are said, if you are given some vector where the curl of V is zero, right? What it means is, so this is again, this is very basic question. So it's said that curl of V is zero. This is how V looks like. How do you find A, B, and C? So this part is quite easy. So what you do is you use the formula of curl of V, and you can equate all these terms to zero. You will get A, B, and C. So you know what V looks like. So nothing interesting about this question, but this part is very interesting. So it is said that if curl of V is actually zero, you can express V as gradient of some scalar function, right? So now how do we prove it? Is consider V to be gradient of some scalar function. So then V becomes del phi del x I cap plus del phi del y j cap plus del phi del z k cap, right? Now, if you equate this to your given vector that you have here, so if you equate, you get this three equations, right? So now if you look at just this equation and try to integrate for phi, so this is a partial derivative in x, right? So you do an integration with respect to x, considering y and z to be your ultimate function phi will have some y and z dependence. So for while we are doing the partial integration, we'll consider this to be constants, but we'll also consider that some other function of y and z can exist, right? So when we do the integration just for this, so what you get phi is equal to x square by 2 plus 2xy. So here 2y is considered to be constant and 4z into x, right? Plus some function of y and z, which we don't know. Similarly, now if you consider the this function, this equation, and try to find phi from here independently, you will get something like this, like equation phi. And similarly, from equation 3, if you integrate, you'll find this expression, right? This is the expression for phi. So now if you compare these three expressions, right, what is this telling you? So that means, you see here you have some terms common, and then you have some generalized functional expressions. So this, if you compare all the three, you'll get the expression for fyz, gxz, and hxy. So that gives you a complete scalar function. So that means if you are given some irrotational vector, you can write it as a gradient of some scalar quantity, right? And such fields, the fields which where you can write it as gradient of some scalar quantity, are called conservative fields, and we'll see how useful this will be, especially in electrostatics, right? In coming slides. Initially, the very concept of potential comes from this. Okay. So if your electric field, if it is rotational, say if curl of E is 0, then from there you can say that you can write E as gradient of some scalar quantity, and it is that scalar quantity which we call as our potential. Okay. So is everything clear till now? If you have some questions, you can ask me regarding what we just discussed, and then we'll proceed forward. Okay. So I'll consider it's clear to all. So now let us talk about Gauss's law. And as you know, in the last class, this is how a field, the electric field will look like for a point charge, right? And you know that this is how the field lines look like. So if you have a positive charge, the field lines are emanating from the charge. If you have a negative charge, the field lines come towards the charge, right? So now what Gauss's law tells you is that given these conditions, if you want to find flux, flux means how many field lines, how much of the field lines are actually crossing your surface. So if you have some surface S and you want to find the flux of your electric field through that surface, how do you define it? You define it as what is your electric field, okay, and surface integral over your surface that you want to find the flux about, right? So this is the, excuse me. So this is the basic definition of flux, right? Now, what this tells you is that if you have some charge inside some closed surface, okay, so you have some surface, closed surface, inside that you have some charge. So you know that if you had some charge like this, so there'll be field lines emanating from all these charges, right? So if there is a net positive charge inside, what will happen? There'll be some net outward flow of fluxes. Similarly, if you have a net negative charge inside, you know there'll be some net negative, inflow of flux lines, right? Field lines. And if you have zero charge inside, what will happen? Basically, if you have such a combination of charge that all the field lines, it starts from one point and goes to the other and it's completely closed inside the surface, then there are no field lines actually leaving the surface, right? So that means in that case, the flux is zero. So that tells you that if you have some charge in some within some enclosed surface, the flux is actually a measure of the charge inside, right? And that is Gauss's law. It tells you that if you have some closed surface, you don't, it doesn't have to be a sphere or anything. It can be any closed surface. And if you have some charge Q inside, then the flux through that surface is actually the Q enclosed by epsilon. So how do you prove it for a point charge? Is that, so this is the field for the point charge. You have a sphere, so start with a sphere, and if you take the surface element for the sphere, okay, and do an integration over the surface, then you get Q by epsilon naught, right? So this proves your Gauss's law. Now if you have a collection of charges, what will happen? You'll have a collection of all the charges inside. Right? Basically, the total charge enclosed is what matters, right? So that's Gauss's law. Now, what we discussed, or this form that you have here is called the integral form of Gauss's law. You can also write it in a differential form. So what you do for that is you use the divergence theorem, which relates surface integrals with, so closed surface integrals with volume integrals. So if you have some vector E, and if you have a surface integral over a closed surface, it's important that it is closed. So if you have a closed surface integral of any vector quantity, you can write it as divergence of the vector into a volume integral of the divergence over the volume that is enclosed by this surface. Okay. So that means now this is your flux, right? And on the other side, you had Q enclosed by epsilon naught. But if you use this divergence theorem, you can write this same surface integral as this volume integral. So now if you compare, you can also write Q enclosed as rho d tau, where rho is your volume charge density. So by comparing, you get to this form. So divergence of E is given as rho by epsilon naught. So this is the Gauss's law in the divergence, in the differential form, right? And it relates the electric field with the surface density, with the charge density, volume charge density, right? So if you are given some question where you know the electric field, you have to find the charge density. So you know which relation to use, right? So just like this question, you have some electric field given, okay? It's in spherical coordinates. You have to find the charge density rho. So what you do is you use this formula, right? Epsilon naught divergence of E. So if you know E, you can find divergence of E. Here you have to use the divergence in the spherical coordinates. So this is something we discussed in the last class, if you remember. Based on the scale factors, you can write expressions for all the different, gradient divergence curl and all the surface element, volume elements and everything, right? So the curvilinear coordinates that we discussed in the last class. So from there, you can get the expression for spherical code for divergence in spherical coordinates, and that is what has been used here. Okay, and you do epsilon naught divergence of E, and that gives you the charge density rho. Okay, now if you want to find the total charge that is contained, so you know what to do, right? The total charge is nothing but rho d tau integration over the entire volume. So you can do that, right? Rho d tau integration over the entire volume. But another way of finding it is from Gauss's law. So there you use the fact that this surface integral is nothing but Q enclosed by epsilon. So you can directly start with your electric field and do a surface integral. So either you do a volume integral or you do a surface integral, right? In volume integral, you use the charge density. In surface integral, you use the concept of flux. So there you directly use the electric field. So given based on what you have in your question, you can use this relations. Now, this is a very standard question, and I think many of you have already seen this question. So here it says that if you have some charge at one corner of the cube, what is the flux through this shaded site? Right? And how you do it is, obviously we will use Gauss's law. So what you do, you first try to enclose this charge because it's on one of the corners. How do you enclose it? So you need to have similar such cubes on all sides, right? So that this point charge Q sits at the center of your new big cube. Okay. And then you can write that for this big Q, your total charge enclosed is Q. So the net flux will be Q by epsilon naught, right? So there, when you consider the total flux, you know it's Q by epsilon naught. But there, what are the surfaces that are involved? So you can see you have 24 such surfaces. You want to find the flux through this surface, but in this bigger cube, you have 24 such surfaces, right? So that means for this 24 surfaces together, the net flux is Q by epsilon naught. So for one such surface, you will have the total flux to be Q by 24 epsilon naught. So similarly, based on, there can be many such questions based on the position of the charge, try to enclose the charge and then use the Gauss's law. Okay. Now, this is another standard question which says that uh, This is a long cylinder which carries a charge density, and that is proportional to the distance from the axis. So rho is a function of your radial coordinate. The radial coordinate is given as s here, right? So it's a function of the radial coordinate. So it's given as k into s. S is your radial coordinate, and you want to find the electric field inside the cylinder, right? So how do you do it? So you actually consider a Gaussian cylinder, okay, and try to use the Gauss's law based on what is the charge that is enclosed, right? So if you consider a Gaussian cylinder of some length L and some radius S, right? And then if you want to use the Gauss's law, you know how the volume element for this cylinder will look like, right? It's S ds d phi dz, right? And then you know what is your charge density. So use that. So that gives you an expression for the charge that is enclosed within this smaller cylinder that you have considered inside the given cylinder. Okay. So that means if this is your charge enclosed, now you can use, you use the Gauss's law. And here you know the expression for the charge enclosed. What you have to do now is to find this surface integral. It's important to consider the symmetry of the question. So here you see that you have charges here, right? So you have to consider the scalar product with the area vectors. So when you consider the curved surface of the cylinder, you know the area vector will be pointed like this, right, along the radial components. And similarly, you'll have, so if you consider this surface, it will have something along this line, along the axis of the cylinder. Similarly, this will be along the axis, while the curved surface will have it along the radial direction, right? So now what you do is, so this is where the symmetry comes in. So that tells you that your E should point radially outward, right? So that means you need to consider the flux along the curved surface, because consider the field lines coming out along all the directions starting from the central line radially, right? So you need to consider the curved surface. So that's where dA comes. So you write it as E into 2 pi SL. You know what is the curved surface area for a cylinder of this given dimensions, right? So that means E into 2 pi SL will be equal to this enclosed charge by epsilon naught, and that gives you an expression for the electric field inside. If it was, suppose if you are asked to find the electric field outside, then you have to consider a cylinder. The Gaussian cylinder has to have a length and radius larger than this given cylinder, right? And then use the same concept. So there actually the total charge of this the cylinder will actually be enclosed in that Gaussian surface. So you can directly use the total charge in by epsilon naught. When you have a similar hollow spherical shell, so I think a question like this is also like this is a similar kind of question I had seen in the previous year assignments. So if you have some particular questions regarding that, you can ask. But so these are basic ways of solving these questions, and you can translate this to your assignment questions. Okay, so here you have a hollow spherical shell. The surface, the volume charge density is given, and you have to find the electric fields in three regions: R less than A, R within A to B, R greater than B, right? So this is a hollow shell. So all the charges that are there is actually in the region from A to B, right? So now if you use the Gauss's law, then you tell me what the field should be at somewhere inside. This should be pretty straightforward, right? Because you guys have been so silent, I'm just hoping you are. These are pretty straightforward things, but it's important that it's clear. So what happens when you consider a sphere? So based on the region that you have to find, you have to choose your Gaussian surfaces, right? So here when you have to find the field somewhere inside, you have to consider a Gaussian sphere of radius less than a, right? And if you consider a surface, such a surface, you know that what should be the charge enclosed? It should not enclose any charge, right? Because there is no charge in this hollow region. So that means for this case, your electric field should go to 0, right? For the second case, now there will be some charge enclosed, right? So you have to actually do integrations using this surface, this volume charge density. So how do you do it? So first part, the electric field is 0. For the second part, consider a sphere somewhere in between A and B, right? So then E into 4 pi r square, if r is the radius of your Gaussian sphere, then E into 4 pi r square will be equal to the charge enclosed by the sphere by epsilon naught. And there you have to do an integration from A, starting from A to r, your Gaussian sphere radius. And if you do that, and then if you use, this is the Gauss's law. So if you use that, you'll find an expression for electric field. And from symmetry, it's clear that it should be in the radial direction, right? And then if you are asked to find somewhere in a region greater than B, then what happens is the total charge that is present in this hollow shell will contribute, right? So everything else remains the same, but now your R is greater than A and B, okay? But because there is only charge from A to B, what you have to do is an integration from A to B to account for the total charge in the hollow sphere. So this is how the field will look like outside the hollow sphere. So if you plot it, it will have a dependence like this, right? So you can have similar questions where, these values are specified. Okay, here it's in terms of some variables, right? A, B, and so now if you have some particular numerical values to A and B, you'll be able to solve, right? Using the same concept. Okay, now when we talk about curl, we did talk about, how the, when we talked about initially about curl of a vector, we talked about how irrotational fields can be written as gradient of some scalar quantity, right? So that's what we are getting to here. So here, when you start with the electric field for a point charge, and now if you want to do a line integral over some line from A to B, so consider 2 points and try to do a line integral from A to B, you take in spherical coordinates, you take a line element, okay, and you do the line integral. So if you do the line integral, what you are doing is basically the dot product between the electric field and this line element, right? Because the electric field is only along the radial direction, you only have the dr term here, right? And then you do an integration from A to B. What do you get? You get this expression, right? Now what happens when you have a circular, not circular, rather consider a closed path. Okay, so you start from A and come back to A. So that means their RA becomes equal to RB, and this tells you that if you have a closed line integral of your electric field here, it turns out to be 0. Now, if we try to relate this line integral with some, with surface integrals. So this is a closed line, right? So that makes a surface. So now if you want to write it in terms of surface integral, you use this Stokes theorem. So what does the Stokes theorem say? It says that if you have some, boundary, some closed boundary, some closed curve enclosing a surface, then the line integral over of a vector quantity over the surface will be equal to the surface integral of curl of that vector quantity in the surface that is enclosed by the curve. Okay, so that means you can write E dot dl, closed integral of E dot dl, as curl of E into ds, and surface integral over the surface enclosed by this closed curve, right? So now what you say is that we know that this is a, a valid thing for a closed path. Now consider this example. So okay, so first of all, from here you can then write curl of E to be 0. Why? Because you can just use this formula. So that means so surface integral of curl of E is 0. That means curl of E should be equal to 0. So that gives you a vector. So now your electric field in this condition, your electric field is such that the curl of the electric field is equal to 0, right? So this now, this is just a definition of the electric potential and how you define it. But first we would go here, right? So because your curl of E is 0, you can write the electric field as a gradient of some scalar quantity, which you call the potential. Now, how will the potential look like? The potential will look like this quantity, right? So then you define the potential in such a way that you say that there'll be some reference where you start with, and if you take your point from that reference point to your field point where you want to actually measure the potential, then this is how the potential should look like. So if you have some some A and B 2 points, you can find the potential difference from here, okay? And then VB minus VA is nothing but divergence of V dot dl over the line. So this is just fundamental theorem of gradients. And now if you compare this to, you would see that again electric field is written as minus grad V, right? So that means this is a scalar quantity potential, this is a vector quantity, and this is how these two are related given your curl of E is 0. Now, because E is minus grad V, now if you use this relation that we had initially derived, and if you put this expression here, you get del square V equal to minus rho by epsilon naught, and this is what is called the Poisson's equation, okay? And in conditions where your charge density is 0, you'll get del square V equal to 0, and this is called the Laplace equation. So any solution, so if you have some, some scalar quantity, and if that quantity satisfies this relation del square V equal to 0, then this quantity, like this function, will be called, okay, why negative sign? This is just a convention, okay? It's just the convention how how it is taken, okay? Basically, you start from a point and you you take a reference, and then you come to the point of your interest. Had it been the other way around, it would have been plus. So it's a convention. Okay. Basically, see, this is some scalar quantity, right? So minus of V is also a scalar quantity. It's just a way of defining. Okay. So now what you get is this Laplace equation. So in I don't know in current assignments what the questions are, but there was one question which spoke about, there was a quantity, I think a vector was given, and it was asked whether it is a harmonic function or not, or things like that, right? So you have to see if it satisfies this relation del square V equal to 0, those functions are called harmonic functions. Okay. And in questions, suppose if you are given the charge density, you need to find the potential, then you have to use this relation. Similarly, if V is given and you want to find rho, you again use the same relation, right? So basically, these are all the relations that we had discussed about so far, which relates the electric field with the potential and the charge density. And based on what you know, you can use any of these relations. Okay, now talking about electric displacement. So why it is interesting is that suppose if you have some dielectrics, right, and if you have some field, some charge nearby, okay, and in your system, if you have some dielectric, there'll be some charge which you can put on your on your system. So you have control over the charge, and that is something free because it's something which you have provided or externally the system acquires. But then there can be bound charges that develop inside the material, right? So if you talk about total charge density, you have contributions from bound charges and free charges, right? So now if you write the Gauss's law, you know that epsilon naught divergence of E is given as rho, and this is a total rho, right? Including both the uh, the bound charge and the free charge. Now, this bound charge is actually related to the polarization of your material, right? So, in presence of some external field, how the charges inside get redistributed can result in polarization. and that is related to the bound charge that can develop inside. So you can write this. So this derivations will also be clearer, if in coming slides, coming classes. But for now, what you can consider is that this bound charge is given as minus divergence of the polarization, okay, that your system has. And then you have the free charge. So that means you can combine this two term, and what you get is a quantity like this, right? So this quantity is called the electric displacement. So now when you use the electric displacement, you can write the divergence of the electric displacement to be equal to the free charge. And this is quite useful because this is the charge which we control. Okay. The bound charge that develops naturally in the material is not in our control. So that means this is your expression for, is the same Gauss's law, but now in terms of the electric displacement. And if you want to write it in terms of the integral form, you'll have again this surface integral. So here you do not have that epsilon term, as you can see, because the epsilon is taken care of here, and you do not have the bound charges because that is taken care of in P, in the polarization, right? So this is how the Gauss's law look like in terms of your electric displacements. So there is a question in your assignment which or there was a question in the last assignment last year, so where we saw that you have a line charge, okay, some straight line with some uniform line charge given by lambda. And then it was said that what would be, suppose you are asked, you have some line charge and you say what would be the uh, electric displacement at some given point, right? So what do? You consider a Gaussian cylinder, okay, a cylindrical Gaussian surface. And then you say that, okay, again, the Gauss's law will be valid in this region. So what you do, based on the symmetry, you know again that the field lines should be along the radial directions. So you use the Gauss's law, you say that if D is my, so at the given point, whatever distance you want to find your, so what I mean is that, if you are given some charge density, and if you are asked to find at some particular distance from it, consider the radius of your Gaussian cylinder to be that distance, right? Just ignore this spike. So consider the radial distance to be the radius of your Gaussian cylinder, okay? And then consider an arbitrary length, okay? Some length L in enclosing some charge, okay? And this is suppose your charge distribution, right? It will have some charge. So that means now if you use the Gauss's law, you know that, there'll be a D, okay? And you know that the curved surface area enclosing this charge will be 2 pi SL, okay? And what should be the charge that is enclosed inside? That should be nothing but lambda into L, right? Now you can see LL cancels out. So what you find is the electric displacement at a distance s from your line charge distribution, right? Now if you consider the region, in a region where there is no insulation. So here in this question it was said that there was a rubber insulation enclosing the wire. Now if you are asked to find the electric field, somewhere out here where there is no such, insulation, which can actually have some bound charges, in that case you can directly translate this or use this to find the electric field, right? So then you can use this relation that E is equal to d by epsilon naught, considering P to be 0. So that is what happens in free space, okay, or in any media where the polarization has to be 0, okay. And then you can use the same relation to find the electric field at a particular point. And if you see, this is what is all can also be derived, and I think this was something which in the last class we discussed about a question where we were saying how does the electric field line go, for a line charge distribution, and what kind of relation does it have with the distance? We said that it has an inverse relation, right? And this is the same derivation, but now we used the Gauss's law. Okay. So now in assignments, these are the same concepts, but now there can be numerical values to it. So if you are said, what I had a question in the last assignment, what I saw was that, some lambda was given as some 8 uh, microcoulomb per meter or something, and then you are asked to find the field at a distance of 5 centimeter or 3 centimeters or 5 meter, something like that. So then you can actually directly put these values in this expression, right, in the expression of the displacement vector, like electric displacement vector, to find the quantity. And it's important to note that it's along the radial direction, which comes from the symmetry as well, right? Okay, so any question till here? Okay. So now we'll try to, okay, there's a, looks like a question. Someone might have been writing something, or if it is cleared, just let me know. Okay, I'll consider things are clear, right? Okay. And if you're asked, try to find the flux. I just remembered there was questions like, suppose similar situations, you're asked to find what is the flux through it. I think in the question that I saw, the units of the answers were like, it was asked to find the flux, but the the units, you can see it's in charge, in units of charge, like coulomb. So basically what they're actually asking is the charge enclosed. So if your length uh, of your cylinder is, if it is known, what you can just consider the same thing, but now because you know the electric field, you can actually just do a surface integral right now with the values. So once you do that, you'll actually find that the charge enclosed is nothing but lambda into L, given your L. Okay. So now let us move to some questions, numerical questions. So here in this question, you have the electric potential in a free space, and you have the expression for the electric potential, where with this functional form fx, which is not known. You have to find fx, okay? And what are the conditions that are given? It is said that the charge density rho is 0, okay? And the x component of electric field is 0, and x component of electric field and the potential are 0 at origin, okay? Now these are the three conditions that are given. You are asked to find fx, right? So how do you solve it? Okay. Now, do any of you have any idea? So the first hint would be that look at what are the conditions that are given and tell me what are the relations that are to be used. So there is a condition with including rho, there is a condition including Ex, and there is a condition including V, right? So if you just first consider the condition with charge density being 0 and your potential is given, okay. Okay. So the talking about reference books, so the electromagnetism part is mostly taken from the theory part is from Griffiths. The vector calculus part was from Swarm series, vector algebra. And these are some questions. So these questions that I'll be currently discussing, they are some previous year questions in CSIR net or some competitive exams. And yeah, that's it. Yeah, I hope it is. Okay. So now the first thing, yeah, thank you. Okay, so now that you have so based on the question, can you tell me, you have the expression for V, okay? And it is said that rho is equal to 0. So first, point is, what expression or what relation rather should we use? Can anyone tell me? So you need to use the expression which involves rho and v. And what is the relation that it should be? Anyone, any answer? Guys, are you following, or is it like, if you're stuck somewhere, some confusion, please let me know. Joyshri. Okay. Okay. Gauss's law. Okay. But what form, right? What expression? There are so many forms of Gauss's law that we just discussed, right? Okay. P equal to minus del V by epsilon naught. Okay. Acha, rho. Okay. Okay. Rho. Rho equal to, there's one mistake here. See, uh, it's divergence of E equal to rho by epsilon naught, right? If I go back, see, divergence of E is equal to rho by epsilon naught. E is equal to minus del V. So that means, put this expression, right? Put the expression of E here. E is minus del V. So what you get is del square V is equal to minus rho by epsilon naught, right? So you actually have to use the Poisson equation. And now, because in the question you are said that rho is 0, what turns out is that's the Laplace equation, right? So you need to use the Laplace equation. Is it clear? So it's not del V into epsilon naught, right? Clear, right? So this is the relation that you need to use, starting with this condition. Okay. Now, that means your Vxy is given. So you can actually try to write an expression for del square V, right? So that's what you can do. So you can write an expression. Okay. So you can write an expression for del square V, and this is what it looks like. Okay. Now the next part of the question says that the x component of electric field at origin is 0. Now how do you find the x component? So you know V, and you know how electric field is related to V, right? E is equal to minus grad V. So that means you can now write an expression for your electric field. And this is particularly, so if you want to write the expression for Ex component, you have to do a derivative with respect to x, right? And this is how it looks like. Now you know that this value should go to 0 at x equal to 0, y equal to 0, right? You put that value and you find this condition, right? Now let us look at the other condition. The other condition says that v should be 0 at origin. So now you directly use this expression and put x and y to be 0. And what is the condition that you get? You get this expression, right? So this is one condition that is provided. This is the other one, and this is other condition, right? Now, in this equation that you have just derived from the Laplace equation, what you can write? You can write an expression for the double derivative of f, right? And then you can integrate it to write the single derivative, right? Now, here you use this second condition. You know that the so df dx is equal to 0 at 0 at x equal to 0 is minus 8. So if you put that condition here, you find the constant. So that means you know the expression for your first derivative of x. Okay. And now you integrate it further. So what you do get? You get the expression of fx with some other constant. What you have to do next is you have to use this third condition. So again, you know the value of f at x equal to 0, that is -4. So if you put that value here, right, you can find the value of C2, and that gives you the value of your fx, right? Is it clear to all of you? Clear, right? So this shows how, how you have to use the relations based on the information that is provided in your question. Okay. Okay. Let's move on. So now in this question, here you see that the electric potential expression is given in in spherical polar coordinates. Okay. You have to find the charge density. So basically the potential is given, you need to find rho. So again, what is the relation that we will use? So I'll share the solution, but I just want you guys to, you know, Laplace equation. So Laplace equation will only be valid when your rho is equal to 0, right? So if I again go back to this expression, see, this is the general expression, right? And then when rho is equal to 0, you get the Laplace equation, right? So what you have to use the Poisson relation, Poisson equation, and you have to find rho given your V, right? So if I now again go back, this is your potential. You know the potential. You have to find rho, right? So how do we do it? This is your Poisson equation. So we have to find del square phi, right? Now, because it's in spherical polar coordinates, you have to use the expression of del square in the spherical polar coordinates, right? So this is the expression that you will be using. So if you do that, this is just, you have to practice this so that you remember the expressions and get used to such uh, numericals. But I'll just skip this details of the steps. Basically, some partial derivatives with respect to r. Okay, so you find the expression for del square phi. Okay, and then you have this minus epsilon naught, and that gives you rho. Now it is asked to find the value of rho at some particular point, r equal to r naught. So just put the value of r is equal to r naught, and that gives you the value of the charge density. Okay. Okay. Now this is another question. Here it says that you have some vector quantity given to you, and there is a circle of unit radius in the plane defined by z equal to 1. So x, y, z at z equal to 1, you have a circle, there's a plane, and there's a circle, okay? And it's a unit radius circle, and the center is at z axis, okay? So it's symmetric about the z axis. And then it said that what is the integral, line integral along the, circumference of the circle, right? Now, okay, correct. Very, very good. Yes, so this is a very good answer. The point is, normal people who are not very, you know, acquainted with vector calculus, what will we normally do? So we'll first start with take a line element on the circle, okay, see what is the distance, what is the functional form of the distance, then do an integration over the entire circle, right? That's the lengthy process. But as answered here very nicely, we will not do so much at the starting. So there can be questions where we have to do that, but for this questions, the first thing that you should first use is you should see
if the line integral can actually be converted into a surface integral, and there if it is easier to solve that. So now you use the Stokes theorem, which says that if you have a closed line curve, then the line integral over that curve is equal to the surface integral of curl of A over the surface that is enclosed by that curve, right? So that means you have to first find curl of A, right? Now if you try to find curl of A, you see that the curl of A goes to 0. So this very well tells us what the answer should be. So if the curl of A goes to 0, that means we don't have to do that integration. This is anyways going to 0. Okay. So be careful about using the divergence theorem and the Stokes theorem in such questions. I thought there's some question coming up. Okay, so I'll consider there is no confusion. Okay. So this is another question. So here you see, these are 4 charges plus q charges kept at the vertices of a square of some side r, okay? And there is a particle of mass m and charge q placed in the plane of the square at a short distance from the center. Now, if the motion of the particle is confined to the plane, it will undergo small oscillations with the angular velocity given by what? You have to find the angular frequency, right? So the question says is that so the question says that you have some square. So this is in no way a square, but consider this to be a square. So now you have charges on these 4 vertices, right? And somewhere at a little distance from, so if this is the center, then at somewhere here, you have a plus q charge, right? So you have the plus q charge somewhere here at a distance a from the center. Now it is said that there'll be some oscillations with the angular frequency and you have to find the angular frequency. So how to do that? First is there are charges on the 4 corners, right? So that means it will exert some force on this, right? So we will first try to find the expression for the force, right? Once we find the expression for this force, what is the condition that it will have some oscillations? So consider the case of, simple harmonic oscillation. So how does the force look like? Force is like some constant into the displacement, right? So in that case, you have some oscillation, right? So this k, so if you write f is equal to kx, this k can also be written as omega square x, right? Where omega is our frequency of your oscillation. So that means if you can find an expression for the net force on this charge and see if the force has some omega square x kind of, you know, uh, expression, okay, then from the omega square, you can find omega, right? That is the question. So what you do, you now it is quite simple. So in this kind of questions, first try to think how to proceed. So the other part of the question is pretty straightforward. So what you do is now you consider, first 2 charges at a time. You know what is the distance, you know how the fields should look like. So by symmetry, you'll see that you'll have the field along this direction, right? Along y. So how will it be? So you know the distance from this plus q charge to this point, right? It is at a distance a from the center. So that gives you an expression for this plus q, plus q charges. Similarly, you can consider the other 2 plus q charges and try to find the resultant electric field. So that gives, so if you now, so here you can see the net electric field points upwards, right? And here the net electric field points downwards. So that means the resultant field for all the 4 charges will be this minus this. So that gives you the resultant electric field. and you know what is the charge, right? What is the force? Force is Q into E. So you know this is your plus Q. So plus Q into the electric field will be the force that this Q will experience due to all the four charges. So now this compare this expression to omega square A, right? A is your displacement from the center. So omega square A is the functional form of F if there is some oscillation. So from here, if you compare, you'll get an expression for the angular frequency, right? So that's how one can address this kind of questions. Now, this is another very interesting question, and I'll urge you to, participate in solving this question because it's interesting. Why? Let me tell you. So first, it is said that you have a circular wire of some radius a in the xy plane, okay, and with its center at the origin, and it is said that it has some charge per unit length, which has an angular dependence. Okay, so lambda is lambda naught. Okay, why is my pointer? Okay, yeah. So it is given as lambda naught cos theta. Okay. Lambda naught is some constant. Theta is the angle measured from the positive axis. Now it is said, what is the electric field at the center of the circle? So in this question, what do you think should be the answer? The answer should be D. Okay. Okay. Why do you say so? Or how, or rather, how do you say so? What is the process? XY plane. Okay. There's a charge. There's a charge. Okay, what does this mean? There's a charge in the XY plane, right? Along a circular wire. Why do you say the electric field will be pointed in the Z direction? So basically the question is that you have a circular wire and then there is a charge distribution. It's in XY plane. There's a charge distribution based on the angle, right? Now you need to find the net electric field at the center of the circle. The fourth option that you say says that the field should be perpendicular to the XY plane, right? But why do you say so? Others? Also, others try to contribute. What do you think it should be? Also, think about this, right? This is an interesting point. You have a charge distribution which has a theta dependence, cos theta dependence. So let us try to look at the question, okay? So here, to start with, at maybe put theta equal to 0. Okay, that means it's along the positive x-axis. So what will be the charge? The charge will be lambda naught, right? What will be the charge at theta equal to 90? It will be 0. What will be the charge at this point? It will be minus lambda naught, right? And now what will be the point charge at this point? It should be 0, right? Now looking at it, think how the field should be. It's a plated wire. You have charges distributed over the wire. Based on the angle, you have different charges. Okay. Think about the symmetry in the problem and how the electric field lines should look like. So see, these questions you can typically, actually solve it. Take a line element, see what is the distance from, take a line element, see the distance. It should be, r, and then do an integration from like over the circle. All these things you can do. But I'll urge you first not to do that and think about the problem. So think about, if you have some positive charge, how does the field lines look like? So here if you have some, this is a positive charge, this is a negative charge, right? So how will the field lines look like from here? You need to find your field at this point, right? This is your field point, point of interest. So consider this charge, okay, a positive charge, okay, all around you will have some positive charge, right? So it will be first positive, positive, gradually decreasing to zero, and then gradually becoming negative, right? So now if you consider some, think of some positive charge, and this is your point, how should the field lines be? And similarly, you have some negative charge here. What should be the field lines here? What should be the direction? Are you guys trying, or should I, you know, tell the answer? Okay, so let me tell you. So see, when you have a positive charge, you know that the field lines should, start from that charge, right? So at this point, you can understand the field lines will be somehow directed in this direction, right? It will start from this charge and go. So, and because it's symmetric, there'll be, so this part and this part, field lines will actually, all the y components will gradually get cancelled, right? Now, what will be the field for this charge, or for the charge element here, if you consider? So there again, for the negative charge, the field lines come towards the charge, right? So if it comes towards the charge, that means the field line for this charge will also have a direction like this, right, at this point. So you can see from here that the electric field line should be directed towards the negative x-axis. Now, if you now look at the options, you can tell that the answer should be A, right? Is this clear to all of you? Okay. So this is the basically the option. You can also do the integral and check it for yourself, but this is a, fun way of solving these questions. Okay. Now a little bit of a, standard problem. So here, what is the potential inside a uniformly charged solid sphere of some radius r and total charge q? So here you know that, you can take a small element on the sphere, okay, and you know that V is given as 1 by 4 pi epsilon rho d tau by r, where r is the distance from this element, from the center to this element, okay, and rho is your charge density. So now you know you can use the expressions to find the distance, the expression for the distance, okay, and do the integration, okay. So if you do all that, you'll find an expression for the potential at, you know, like the expression for the potential, first of all. Now here you can put the expression of rho. Rho is nothing but volume charge density, and then you can write the potential in terms of the, the total charge, the radius, and yeah, that's it, right? So this gives you the value of the potential inside and, you know, also on the surface. So how? So on the surface, you have to put R equal to R, right? So if you put R equal to R, you'll see that on the surface, you get a value of, so this becomes 1, right? So it becomes Q by 4 pi epsilon naught R. So if you have a uniformly charged solid sphere, the potential on the surface is given as Q by 4 pi epsilon naught R. and that is a constant potential surface, right? And somewhere inside, so now if you consider the point r equal to 0, so suppose at the origin, the center of the sphere, what will be the value? The value will be 3q by 8 pi epsilon naught r, right? These values come very handy. So if you consider a uniform charged solid sphere, what is the field at the origin or at the center? It's given as 3q by 8 pi epsilon naught r, and on the surface it is given as q by 4 pi epsilon naught r. Anywhere outside, then you can consider the total charge enclosed and use the Gauss's law, okay, and find an expression. Now, we'll use the last result in this question. So here you have two uniformly charged insulating solid spheres, okay, A and B. As you can see, they are both having the same radius A, and they have A has positive charge, B has negatively charged, is negatively charged, okay, and they're touching each other. Now you need to find the potential at the center of the A sphere, and you have to find the potential at the center of the B sphere, and then you have to find the difference between the two, okay. Now it's important to remember that potential is a scalar quantity, and it does follow or does satisfy the superposition principle, right? So that means in this question, if you just want to find the potential at the center of this sphere, you will have a potential because of the charge of the sphere A, and it also have a potential because of the charge of the center B, right? So can you try to tell me what the expression for VA will look like? So what is the potential at the center of A because of the charge on the A sphere? We just derived the expression, right? It's 3q by 8 pi epsilon naught r, right? This is what we got. And what is the potential at the same center, same point for this sphere? So now you have a minus q charge, and you are located at a point 2a distance from your sphere, right? If you consider the effect of just this charge at this point is outside this charge at a distance 2a. And what is the total charge on this sphere? It's given as minus q, right? So now you can use the Gauss's law. So what do you see is that the potential at VA at the center of the sphere A is given as 3q by 8 pi epsilon naught A minus q into 4 pi epsilon naught into 2a, right? So this is what you get. Similarly, you can find the potential for VB. So it's minus 3q by 8 pi epsilon naught A plus q into 4 pi epsilon naught into 2a. So here you have plus because it's plus charged, positively charged, and this was negatively charged, right? So be careful about the charges. And then, so now you get an expression for V and VB, so you can find the difference. So then you know what the answer is, right? So this is your answer, right? So remember that potentials are scalar quantities, and you can use the superposition principle. Be careful about, you know, having the contribution of all the charges that, or all the charge distributions that's there. Okay. Okay. So I think that is it. Okay. So thank you. Any questions regarding anything that we discussed? Okay. So I think then that's it. Let's call it a day. Thank you. Thank you. Thank you. Stop sharing. Bye. Thank you.